So today's unit that we are going to start is the chemical bonding unit. Is the unit that occurs between, or that where we look at what happens when two atoms get close enough and they can actually form some type of a bond. And from previous science courses, you might recall that there are ionic bonds and there are covalent bonds. Ionic bonds, which is what the majority of today's lesson will be about, are where electrons are transferred from one element to another element, usually the less electronegative element to the more electronegative element, and we end up with ions being formed. Ionic bonds usually occur between a metal and one or more nonmetals, and that's really important to keep track of. So remember, on your periodic table, where that stair-step line is, everything over here is a metal, and everything over here is a nonmetal, and you got that weird guy right there who's also a metal. Then we have covalent bonds, which are where electrons are shared between two nonmetal elements. And when they're shared between two nonmetal elements, what ends up happening is that you have two types of bonds that can form: a polar covalent bond and a nonpolar covalent bond. In a polar covalent bond, electrons are shared unequally between two nonmetals. And in a nonpolar covalent bond, the electrons are shared equally between two nonmetals. And we will spend a lot more time with that as we go forward, and have a lesson on that tomorrow. So what we really need to do is focus a little bit on how we know what type of bond is being formed. One way that we know the type of bond that's being formed is by using something that we call electronegativity differences, or END. So there's a general format. So we have ionic bonds over here, and we have polar covalent bonds over here, and then nonpolar covalent bonds over here. And so the issue is that with the polar versus nonpolar versus ionic bonds, there's something that we can do to identify what the actual bond is. So we basically will take the electronegativity difference, and we will determine by subtracting, very simply, what type of bond it is. So nonpolar bonds usually have an electronegativity difference from 0.4 to 0.0. Polar covalent bonds have electronegativity difference from 0.5 to 1.6, and ionic bonds tend to have a electronegativity difference of 1.7 and up. So you'll get that information from your periodic table. And the periodic table that you should have in your possession has the electronegativity differences already written. I believe it's in the lower right-hand corner, so that should make your life a little bit easier. So, calculating electronegativity differences. Here we have chlorine and chlorine, and chlorine, so they're two nonmetals, and so they're two nonmetals. And as a result of that, I can predict pretty accurately that they are going to be a nonpolar covalent bond, but the way that I check to make sure that I'm right is I go ahead and I look for the electronegativity of chlorine. So in this case, I'm going to take the absolute value of chlorine, which is 3.0's electronegativity, minus 3.0, and I'm going to get a value of 0.0, which falls in the range of a nonpolar covalent bond. We then have an element like sodium, which has an electronegativity of 0.9, and fluorine has an electronegativity of 4.0, and when I subtract that out, I get something like 3.1. So because that's above 1.7, I get an ionic bond. And then we have nitrogen and oxygen, and in this case my electronegativity of nitrogen would be 3.0, and the electronegativity of oxygen would be 3.5, and I get a difference of 0.5. So that tells me it is a polar covalent bond. And that's all that's to identifying whether or not an atom, or not an atom, but whether or not a bond is polar, nonpolar, or ionic. And like I said, we are going to spend time today talking about that in a minute. Now, we have to review drawing Lewis dot structures, and you might remember that the Lewis dot structure for an element is based on the number of valence electrons. So if I look at an element like, say, I don't know, sodium, sodium has one valence electron, right? And so when I write its Lewis dot structure, I get Na and just one dot. I know its number of valence electrons is based on its electron configuration: 1s2, 2s2, 2p6, 3s1, and that's the one valence electron. Then we have things like, I don't know, let's say aluminum, which has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p1. So that tells me that because the third energy level is the highest energy level, that I have 3 valence electrons. So when I draw that structure, it would look something like this: 1, 2, 3. And I'm just spreading those electrons out as far as possible before I double them up. And then, speaking of doubling them up, let's take a look at something like fluorine, for example. Fluorine has an electron configuration of 1s2, 2s2, 2p5. So the highest energy level is the second energy level, which means that I have 2 plus 5, so 7 valence electrons. So that tells me that I'm going to take fluorine and I'm going to put 1 electron, 2 electrons, 3 electrons, 4, 5, 6, 7. So I've got pairs of electrons. I think that's a review from last semester, and if it's not, hope that it wasn't too hard. Generally, an atom that has 8 valence electrons, something like neon, would have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And then that would be a full octet, which is really important. Speaking of which, all atoms bond to create a more stable arrangement of electrons. So if they're going to create a more stable arrangement of electrons, they're doing so that atoms have 8 valence electrons if possible. So in the case of like lithium, right, I'm telling you that this is an ionic bond, but the issue is that I'm going to check, first of all, that lithium has an electronegativity of 1.0 and fluorine has an electronegativity of 4.0, so the absolute value of that is 3.0. So yep, it checks out. It is absolutely an ionic bond. So when I draw these structures, what I do is I go ahead and I first identify the number of valence electrons. Well, lithium has, according to the periodic table or the electron configuration, 1 valence electron, and fluorine, according to the periodic table or the according to the periodic table or the electron configuration, has 7 valence electrons. So what I do is I draw lithium with its 1 valence electron, and instead of doing a dot, I'm going to do an X just so I can track it. You can do dots. I'm just going to do an X. And then fluorine has 7, so I'm going to do dots for fluorine. And because the electron is being transferred from the less electronegative element to the more electronegative element, because that's the point of this, I need to draw an arrow that indicates that the electron has transferred to fluorine. So that's the process. Now, when I draw the structure, I'm going to write lithium, and lithium has lost an electron, and when it loses an electron, it goes from being neutral, right? So lithium had, lithium had protons, neutrons, and electrons. So lithium, according to the periodic table, has 3 protons and 3 electrons, so it lost an electron, right? So if it loses an electron, it now becomes a +1. So I have to show that +1 right there. And then fluorine has gained an electron, so that looks something like this. And I'm going to keep that red X there just so I can see where it happened. So now fluorine went from having 9 electrons, 9 protons and 9 electrons, to having 9 protons again and 10 electrons. So that means fluorine has a -1 charge. And if you look at it, it appears that lithium has lost its clothes, so I sometimes refer to that as being naked, and fluorine has completely been clothed. You can't see any skin on fluorine, so it's fully clothed. So we need to see that. And then you will finally write the formula, which in this case is LiF. So hopefully that wasn't too bad. One more example for you. Well, looks like 2 more examples for you. First of all, this is ionic. I know it's ionic because sodium's electronegativity is 0.9. Sulfur's electronegativity is, let's see, according to my periodic table, is 2.5. 0.9 minus 2.5 is, what is it, 1 point, math is hard tonight. 2.5 minus 0.9. Oh boy, 2.5 minus 0.9 is 1.6, which puts it right on that edge, but because it's a metal and a nonmetal, I know it's ionic. So, sodium has 1 valence electron, and sulfur has 1, 2, 3, 4, 5, 6 valence electrons. So I'm going to draw the arrow of transferring 1 electron to sodium. So that arrow would look like this. But at this point, sodium has lost its 1 electron, and it's a +1, and that's good. But sulfur isn't satisfied. It doesn't have 8 valence electrons. So if I were to draw that right now, that would look like this. That's my cat. So sulfur is short in electron. Hang on, sorry, I got a little carried away. So sulfur is short in electron, so that means I have to add another sodium to this ionic compound. And now by doing that, I now have sulfur with 8 valence electrons, but now sulfur has a -2 charge. And when I write the formula for this, I go back and look at the process and see that I have sodium, and I've got 2 of them, both naked, and sulfur, which is completely clothed, so I get Na2S, which again, hopefully is not so bad. So I got one more example for you, and that's aluminum. And aluminum, according to the periodic table, has electronegativity of 1.5. Oxygen has electronegativity of 3.5. Select a 2.0, so that's definitely ionic. So I'm going to take my aluminum, which I know has 1, 2, 3 electrons, and my oxygen, which I know has 1, 2, 3, 4, 5, 6 electrons. And I'm going to start the process by drawing an arrow. And when I draw one arrow, the oxygen is not satisfied and aluminum is not satisfied, so I'm going to draw another arrow. At this point, I've produced an oxygen with 8 electrons around it and a -2 charge. But I still need to get aluminum to only have, to get rid of that last electron, so I'm going to add another oxygen, which, as we've already drawn, looks like this. And I'm going to transfer an arrow right there, or transfer an electron right there. So at this point, I have an aluminum that is completely closed, lost 3 electrons, so it's a +3. Okay. My oxygen, though, has only gained 1 electron, so it's not satisfied, so I need to add another aluminum. So in adding another aluminum with 3 valence electrons and draw the transfer, I now have an oxygen that has the 8 valence electrons and its charge is a -2. But now aluminum's not satisfied, so I need to add another oxygen. So in this case, 1, 2, 3, 4, 5, 6, and I'm going to transfer an electron here and an electron here, which will give me that third oxygen with 1, 2, 3, 4, 5, 6, 7, 8. So it's now a third oxygen with a -2, and the aluminum is naked again with a +3. So when I count this all out, I see that I have Al2O3. Okay. So your homework is the first worksheet in the packet. I believe it's a two-sider. So as a result of that, you should be able to identify the different types of bonds, ionic, covalent, or polar, or covalent, nonpolar, and be able to draw what happens in an ionic bond.